In this short video, we'll dive into some of the theory of the Markov decision process, or MDP. We'll begin understanding the probabilities involved in this process. But first, what is a Markov decision process in the context of reinforcement learning? Let's take our grid world environment as an example, and let's create a sequence that is a Markovian process. Let's say that the agent starts in the state S0 and executes its first action, let's say go down, and now he enters a new cell, S1, and receives a reward, R1, for entering that state. Now the agent executes the next action, let's say go right. He enters the next state, S2, and receives the reward, R2. And we keep going, let's say to the right, enter the state S3, receive the reward, R3, and now we go up, enter the state S4, and receive the reward, R4, and so on. The agent continues moving across this environment. Now, those interactions of the agent with this environment give rise to this whole trajectory composed of consecutive states, actions, and rewards. And we say that such a process is Markovian when each consecutive state transition only depends on the agent's immediately preceding state and not on any other past state. In other words, any choice of the current transition is not influenced by where the agent was in the past. And we also call such systems as not having a memory of the past. But what we have shown here and what we've been dealing with so far in this video series are deterministic environments. That is, when the agent chooses a particular action, it actually executes that action with certainty. And when the reward is to be given to the agent, it is also given with certainty. And this doesn't have to be the case in more complicated environments that more closely resemble how the real world functions. We might want to, for example, model some kind of malfunctions of the agent's movement and some imperfections of the rewarding system. For example, coming from time-lagged response times, that even though they should return a reward, they don't. And we can implement all of those imperfections by introducing the notion of this probability distribution P. And this links with the discussion from chapter 3 from this great reinforcement learning textbook. And while this textbook is very rigorous, I found it difficult to grasp the importance and meaning of this probability at first, so I wanted to make this video to show you a couple of illustrative examples to make this probability more grounded and linked to our grid worlds. Now, this P is a joint probability over two variables, S prime and R. So it's a probability that we will enter the future state S prime and receive a reward R. And this probability is also conditional on S and A. That's what the bar denotes. It's conditional on. And overall, you can read this whole thing as a probability that the next state will be S prime and the reward will be R, given that, that's what the bar denotes, given that the current state is S and the action selected is A. And notice that this agrees with the notion of a Markovian process because the future state, S prime, only depends on the immediately preceding state, S, and not on any other past state. So let's pause here and see what's the consequence of introducing such a probability. Let's say that currently the agent is located in the state S, and he chooses an action to go up. And he enters this state, S prime, as the future state. And let's say that also the reward for taking that particular step is equal to 1. So you may wonder, why would probability of entering S prime be any different from 1, right? Or why would the probability of receiving this particular reward be any different from 1? And so far we've only dealt with the state transitions and rewards that were certain. So it feels natural to ask these questions. But the answer is that they don't have to be certain. And by making them uncertain, we allow for all sorts of imperfections to enter our reinforcement learning tasks. And when the dynamics of the environment has some level of randomness to it, we say that the environments are stochastic instead of deterministic. So let's look at an example 2D grid world that would not have certain outcomes. Let's say that our grid world only has 5 states. In this case, the set of all states has 5 elements. And let's say that we only have 3 possible reward values, -1, 0, 1. So the set of all possible rewards has 3 elements. And this, by the way, defines a finite Markov decision process, a finite MDP. And a finite MDP assumes that there is a finite number of both states and rewards. Potentially, there can be infinite number of states in the environment, and or rewards can be continuous and therefore infinite. But you may imagine that dealing with infinite MDPs will be different than dealing with the finite MDPs. So we will leave that aside for now. And let's say that our agent starts in this state as 0 and chooses an action go up. But let's say that only 90% of the time he will actually go up. And instead, 8% of the time he might steer to the left or to the right. 1% of the time he might go down, and 1% of the time he will actually stay where he was. Now, this placement of probabilities accounts for possible malfunctions of our agent and can, for example, mimic an electronic robot malfunctioning sometimes. Or it may mimic a living organism, say a bacteria, acting unpredictably. Now, what about the rewards? Well, the rewarding system can malfunction too. So let's say that 90% of the time, if the agent indeed goes up, he will receive a +1 reward. But let's say that 8% of the time he may receive 0 reward, and 2% of the time he might actually get punished by a -1 reward. Now, to complete this environment, we also specify the probabilities for the 3 rewards for all the other states, even for the state as 0, just in case the agent remains there. And this type of environment is called a stochastic environment as opposed to deterministic. And these probabilities attached to this environment will define the dynamics of the Markov decision process and hence the dynamics of how our agent learns to maneuver this environment. As one last thing here, let's try to understand the following statement. When we sum those probabilities across all the future states and across all possible rewards, we should get 1. And this sort of makes intuitive sense when you think that among all possible future states, entering either of them, whichever it is, has to be a certainty, right? In other words, with certainty, we will end up in some future state. And we will be rewarded by some future reward, although we might not know with certainty which state and which reward it will be. But let's dissect these summations a little further. In the case of our example grid world with just 5 states, this first summation will go over 5 elements from S0 to S4. The second summation will go over 3 elements, -1, 0, and 1. And notice that these probabilities can potentially be 0 for some states and some rewards. And this can model the fact that some future states might be completely unreachable from the current state. Say we had, for example, this extra state S5 over here, which cannot physically be reached from S0. And in this case, this summation will go over 6 elements, because now we have 6 states in this environment. But the probability of entering S5 from S0 is 0. And let's practice computing those joint probabilities a little bit. Let's do a summation over all 3 rewards, but for just one state transition. So from S0 to the future state S1. So the first probability will be that of entering S1 as the future state and receiving reward R equal to 1, given that the current state is S0 and the action selected is to go up. So this will give a 0.9 probability for this particular state transition and 0.9 probability for this particular reward. So 81% chance. And notice that we could simply multiply these probabilities because we assume that the state transition and receiving the reward are independent events. The second probability is that of entering S1 as the future state and receiving 0 as the reward. So this is 0.9 chance again times the 0.08, so 8% chance of receiving that particular reward, so 7.2% probability. And the third probability is that of entering S1 and receiving the reward -1. So this is 0.9 chance again, times the 2% chance for this particular reward, so 1.8% probability. And notice that if we now sum those 3 probabilities, they give us 90%, which is equal to this state transition probability. So if we now do the complete computation and also sum across all of the possible future states, we should get 100%, right? We will get 1. Okay, so in the next video, we'll keep going with the Markov decision process. See you then.